Hello, everyone. I'm so sorry. Hello, everyone. I'm so sorry for logging in late. I have an alarm set that's supposed to go off like 3 minutes before class starts, and I forgot I turned it off Monday because we were off, and then forgot to turn it back on today. So I apologize. If I end up running over at the end and y'all need to leave, go ahead and split. Just remember the last, if you miss 5 minutes or whatever, then that'll be on the video, so you can still just go fast forward to the 5 minute mark or 5 minute from the end mark and watch whatever you missed. So don't feel bad if you have to leave. Again, I'm real sorry about that. Anybody have any questions before we get started? Oops, did not mean to do that. No questions? Okay, so remember you have a test. Hopefully y'all saw the email on Friday, but you have a test that was due tonight at 11:59 p.m. But I did push it back to the 10th at 11:59 p.m. So make sure you get it done by then. What I would recommend, if you haven't already taken it at least once, go ahead and take it once, like today or tomorrow, and then knock out the other trials on Friday. Because if you don't get one in, there's a good chance you might completely just forget, and you don't want to waste your drop test on a 0 that you just forgot to take. So make sure y'all get that test done. Again, does anyone have any questions? Now it looks like everybody's logged in. All right, well, I guess I'll just get started with chapter 3. So chapter 3 is on projectile motion in 2 and 3 dimensions, semicolon, vectors. So the big part of this is vectors. That's one of the ongoing themes of this course is you will deal with vectors a lot. And in fact, when you take the second semester, you'll be dealing with vector calculus, which you'll learn basically from your physics instructor in this case, or some cases you'll learn it from your statics instructor or something like that. So that's the normal thing with people that major in science or engineering. You're often going to learn your math from your physics or engineering instructors before you ever get to it in your math. For instance, I took a differential geometry course, and literally the first day of my general relativity course, we covered covariant derivatives, and the very last day of my differential geometry course, we covered covariant derivatives. So that was a bit problematic, but that's the nature of it. So just be prepared. The good news is I take pride in showing you all the gory details so you can figure out exactly how things work. And in most cases, it's a really simple scenario for this level course. So one thing I want to remind you about is the 3 special triangles, because I use those a lot to keep me from having to do calculations. So one of the special triangles is the 45, 45, 90. I'm going to show you this in a second. I just decided not to show you anything but top of my head for some reason. Everybody's curious what top of my head looked like, I guess. So the 45, 45, 90 triangle is basically a triangle that has 2 legs that are the same. And then, of course, the Pythagorean theorem says that's square root of 2, which is about 1.414. So that's kind of helpful. Then there's the 30, 60, 90 triangle, which you can tell looks almost exactly the same as my 45, 45 triangle. So this would be 60, this would be 30. The angle, the big angle is always opposite the bigger side. So this one has to be the square root of 3. This one has to be 1, and this has to be 2. The square root of 3, if I remember correctly, is about 1.73. Let me double check just to make sure. I want to get a couple extra digits, in other words. So 1.732. Okay, that's what the square root of 3 is approximately. Then another triangle that we use on occasion is the 3, 4, 5 triangle. And this one is about 53.13 degrees. And this one would be, of course, 36.86. Let me erase that. So those are 3 special triangles. I have some other ones I use that are perfect squares, integers, and stuff like that, but they have weirder angles. But these 3 I use a lot, so it's really helpful to have them. I'm sure y'all all somewhat familiar with them. Now that we have those, you can sort of make some sense of some of the quick problems I solve without having to use a calculator. Because usually when I'm using the calculator, I want my students to do the same thing with their calculator so that they can confirm that they got the same calculation I did. Well, students don't always do that for me, so I've decided that maybe it's best if I just make sure I get the right answers by using special angles. So we're going to talk about vectors now, and I want to reference my favorite movie. It's such a favorite movie that my daughters bought a copy of it for me for Father's Day. It's called Despicable Me, and in that first one, Despicable Me, the main bad guy character. Does anybody recall his name? Feel free to chat it if you don't have your speaker.
Vector.
Vector, exactly. He said, it's a mathematical term. And basically what he was saying is a mathematical term that means something with magnitude and direction. He said, because I do evil with direction and magnitude, right? So that's kind of a funny character, but it turns out it's actually correct, okay? That is the definition, or a definition of a vector. It's a quantity that has both magnitude and direction. It actually is a subset. It's actually a small part of a bigger thing called tensors, and tensors are, in some sense, a small part of a bigger thing called differential forms. But the main thing about them is that they are things that exist independent of coordinate systems. And in fact, when you write an equation, for instance, in tensor form, and you switch from one coordinate to another, you automatically get the exact same equation. And that's why Einstein had to go back and study it again, even though he had a course in it in graduate school. He had to go back and study it again when he was coming up with his general theory of relativity, because he realized the laws of physics are the same for all inertial observers would become the laws of physics for all observers. And that meant all coordinate systems should have the same laws of physics. So he had to find out about tensors. So anyways, we won't go any further than that regarding tensors and all sorts of other neat little number type things. But I will tell you that there's a bigger term called algebra than just, the class where you solve for X. There is a bigger concept called an algebra. And those rules that you learn, like the distributive property, the associative property, the commutative property, all those things that have those rules, any kind of sets that you define that obey those rules is called an algebra. And in fact, there's a vector algebra and there's a matrix algebra, both of which are things you ostensibly worked before because you had a pre-calculus class that was supposed to go over vectors to some extent. But the difference is, like in matrix algebra, they don't have a commutative property of multiplication because it's what we call a non-abelian algebra or a non-commutative algebra, because A times B, not only is it not necessarily equal to B times A, it might not even exist. If A times B exists, that doesn't mean B times A exists at all. So neat little stuff like that. So with that idea in mind, I want to tell you, we can do a faithful representation of vectors by drawing arrows. You could even do a faithful representation of vectors by building physical arrows. And what you do is you realize they have to have magnitude and direction. So if you take an arrow, let's pretend this is an arrow. See the pointy end here? That could be the arrow head. And see the dull end back here? That could be the arrow tail. And then the length, using some scale, this length will be proportional to the magnitude of the vector. So for instance, maybe this is 9 centimeters in length. Maybe perhaps you want it to represent a 90 Newton force. then what you'd say is 9 centimeters on paper or 9 centimeters on my pen is equivalent to 90 newtons in reality. Now you have an identity statement, so you can make a fraction out of it and convert with it like units, where you can convert back and forth from real things to paper things and so on and so forth. So that length of that vector can be represented by the length of the arrow. Similarly, the direction of the vector, pointing always from the tail towards the head direction, that can represent the direction of the vector. So we're going to do some stuff today where we're actually going to use drawn vectors, and I will show you ways to add vectors, to subtract vectors, to multiply vectors by scalars. And then with all that, then we can show you an algebraic way of doing it. I will tell you that with the graphical way, by drawing them, if you're really, really meticulous and use a really good protractor, like one that's marked to individual degrees, and you're very meticulous about it, and you use a very fine tip pen or pencil, and you use a very good straight edge and ruling device to measure distances properly, and you translate your coordinate system from one end of a vector to the next end, and so on and so forth. When you're all done, you can't actually work out the sum or the difference of vectors or the multiplication of 2 by a vector or whatever, and get answers that differ by, on the order of 1% from the reality. If you happen to have access to AutoCAD, you can do the same thing, but in fact, we'll have 0% error. Assuming, again, we're on flat space, but that's pretty much all we're doing. So let's get started with talking about vectors and how they can be represented. And I'm going to show you a few things. And from that, we'll hopefully add a set of vectors today. So here we go. I'm going to turn on my document cam. So we normally represent vectors, like I said, with arrows. And when we want to write them handwritten, we usually put an arrow over top of their symbol. We use a capital letter and we put an arrow over top of their symbol. Your textbook and other textbooks usually make it bold print if you're talking about a vector quantity. Some books even go so far as to do bold print and vector and an arrow over top of it. So first off, you might think of a vector as this little thing. Notice I haven't drawn any kind of coordinate system. This vector exists with or without a coordinate system. I'm going to call this vector A. That's what I mean by an arrow over it. Some people even take the time to do a double-headed arrow like that. Okay. Now, one of the things you need to know is what happens if I multiply that vector by a scalar. Well, if I multiply it by the vector 2, by the scalar 2, then I get a vector that's parallel to it, even if it doesn't turn out parallel to it because I'm drawing it by hand, but whose length is twice as long. So that's the vector 2a. Notice the length of this one is twice as long as the length of that one. Similarly, if I multiplied a by 1/2, then my vector would look like this. So I think you can see a little rule right now. The rule is that when you multiply a vector by a scalar, you seem to only change its distance, its length, its magnitude. And if that scalar is bigger than 1, you make it longer. If that scalar is smaller than 1, you make it shorter. And that's actually true. However, we can also multiply it by a negative number. So for instance, if I do this, then this is negative 2a. So see what I've done is I multiplied the vector by not 2, but negative 2. What that did is the 2 made it twice as long, but the negative added 180 degrees to it. So you can say added or subtracted 180 degrees. So that's what a negative sign does. So if I wanted just, for instance, negative a, then that would just look like this. Oh, sorry. I don't know why I reverted to doing that, but anyways. Okay, so if I wanted negative a, notice it's the same length as a. It's anti-parallel to a. You can sort of think of it as parallel because they're along the same line, but the tail to head is the opposite direction as the tail to head in this one. Does that make sense to everyone? Now, there's ways we can represent these vectors in number form. And for instance, what we often do is we draw an XY coordinate system. So this could be X, this would be Y. Notice if I point my fingers like this, I put this in the direction of X and this in the direction of Y, then my thumb, which points straight up using my right hand, has to point in the direction of Z. Always make your coordinate systems that way with your right hand, or it'll really mess things up if you have to do cross products and stuff like that. Now, this often is used as north, in which case this would become east, this would become south, and this would become west. But it's also called a compass heading of 0 degrees, which means this one would be 90 degrees, and this one would be 180 degrees, and this would be 270 degrees, and then back to north would be 360 degrees. Okay, so once we draw a coordinate system, then we can actually express vectors as things with magnitude and direction. So you could say, for instance, the vector A is, let's say its length is 10.0 newtons at 50 degrees. Well, what does 50 degrees mean? Well, if I don't say anything else, I just say at 50 degrees, then we're going with the mathematical definition of an angle, which is measured counterclockwise if it's positive, clockwise if it's negative, from the positive x-axis. So that this one means turn through 50 degrees counterclockwise from the positive x-axis, and that would be the direction of A. Okay? But that could also be represented as 10.0 newtons at, in this case, you could say it is 50 degrees north of east. You could also say it's 10.0 newtons at 40 degrees east of north. Notice how if this is east, if I go north of it through 50 degrees, I get the same thing as that 50. Whereas if this is north and I go south and I go east of it 40 degrees, then that's the same as this 50 degrees as well. So that's 3 different ways I can report it. There's another way as well. I could also say 10.0 newtons at compass heading 40 degrees. Okay, because the way the compass is supposed to work, at 0 at north, and once I got to the vector, I moved down 40 degrees because this would be 90. So 40 degrees would also be the compass heading. So do you see all the different ways we could actually express this vector? And that's in magnitude and direction format. Now you should be able to use all these formats and be able to flip back and forth between them at the drop of a hat. I'm going to show you another way of expressing it. For instance, we could say vector B is, let's say, 3.00 meters I hat plus 4.00 meters J hat. And I could actually include the z-axis and call that plus 5.00 meters k hat. So this is in unit vector notation, and the unit vector I hat is supposed to be 1 unit long, not 1 meter, just 1 number long, and it points in the direction of the positive x-axis. So if I multiply a number from it by it, like I learned up here, then I just make that into a vector that's 3 times as long as I hat, or 4 meters times as long as J hat, or 5 meters times as long as K hat, right? So that's another way. Some people prefer not to use I, J, and K, so they call that 3.00 meters x hat plus 4.00 meters y hat plus 5.00 meters z hat, and that's perfectly acceptable as well. And then some people like to save paper and would write it as 3.00, 4.00, 5.00, and then put the little meter outside. By using a less than symbol and a greater than symbol as brackets, then everybody should know that's in fact the same thing as the notations that you see above. Okay. Any questions on that? Now, if you tried to draw this vector B, you could actually do it, but since the vector B actually has a K component or a Z component, we'd have to draw it in 3 space. So I'm going to draw that for you real quick, just to give you an idea of what it looks like. And then I can even introduce you sort of to the coordinates that you use from spherical coordinates, and that'll make some sense to you then. We don't require you to know spherical and cylindrical and polar coordinates for this class necessarily, but if you do, it sometimes makes life a lot easier. So let me go ahead and draw. I'm going to draw, in this case, the y-axis this way. The x-axis is going to be coming out of the board. And then the z-axis is going to be vertical on the paper. Notice that does agree with my right-hand rule. If I pointed my index finger at me, my middle finger would be pointing in the positive y direction, and my thumb would be pointing up in the positive z direction. So what I'm going to do is mark off units 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So first off, I want to go 3 units in the x direction. That would be right about here. Then I want to go 4 units in the y direction. 1, 2, 3, 4. That would be right about here. Notice I'm trying to draw a line parallel to this axis, just like I tried to draw a line parallel to that axis. Now, once that I have that, I want to go up 5 units. 1, 2, 3, 4, 5. And if I connect that, I'd like to draw a line parallel to that. And then straight up would be parallel to the z-axis, like this. And lo and behold, we have our vector. It points from the origin to that point right there. That's the vector B. Okay. I think you can see that this angle right here, which is one we would call theta in spherical coordinates, and this angle right here, we would call phi in spherical coordinates. And then, of course, just a distance from the origin to there, we'd actually call r. And I think you can tell that, in fact, that one should be 5 times the square root of 2. That should be how long that vector is. Since this is 5 right here, because this is a 3, 4 triangle, see 3 and the 4, then this must be 5. And then this, of course, is also 5. Since that's 5 and 5, that's the 45, 45 triangle. And the 2 sides would normally be 1 and 1 and square root of 2. So this is going to be 5 and 5 and 5 times the square root of 2. So I can now conclude that B is equal to 5 times the square root of 2 meters. And then it would be at theta equals, notice this is 4 on this side and 3 on that side. So that's the big angle, 53.13 degrees. And phi is equal to, notice this one will be 45, but since 45 cuts to 90 in half, this one would also be 45. So I'll say 45 degrees there. So that's another way we can express it exactly the same. Any questions on that? Okay, so now that we have sort of that nomenclature out of the way and we've multiplied vectors by scalars, at least physically, we haven't actually done it with these numbers, but I can tell you what happens if you take vector A and multiply it by 2. Do you think you're going to change this 50 by going from A to 2A?
No.
Nope. In fact, all that's going to happen is you're going to multiply this by 2, so that'd be 20 newtons at 50 degrees. If I did 1/2 A, it'd be 5 newtons at 50 degrees. Now, if I did -2A, it would still be 20 newtons. Notice there's no negative magnitudes of vectors, okay? It would still be 20 newtons, but now instead of 50, it'd be 50 plus 180. So that's 230 degrees. So -2A would be 230. That means literally go up here to 50 and then turn another 180 and you'd be at 230, pointing something down like that. Okay. With these guys, if you multiplied this by 2, then it's just like the distributive property. That means this is going to become 6, this is going to become 8, and this is going to become 10. Same thing with these 3. Okay, so that's how you actually implement these in a magnitude and direction scale or system, or in a unit vector notation. So this was called unit vector notation. Let me go ahead and write that down. Now, not all trig classes, or excuse me, not all pre-calculus classes get to I, J, and K, but they're supposed to all at least get to doing vectors where you talk about magnitude and direction. So hopefully all that's fairly familiar to you. If it's not, that's okay. We're teaching it to you. The textbook tries to teach it to you as well. So we should be able to work just fine. Now what I want to show you is adding vectors. So I'm going to go to adding vectors. And I will tell you that adding vectors is best represented by thinking about the short, straight walks you take when you leave your front door. So let's say you walk out your front door of your house. Maybe your house faces east, in which case you walk due east for maybe 10 meters. Okay. Now you're not walking zigzag patterns, right? You're probably walking straight lines. So that's a really nice representation of a vector. You can just draw a vector that's 10 meters long and points due east, which would be right along the x-axis. But then maybe you take a right. And of course, if you're walking due east and you take a right, that means you're going to be going due south. And let's say you walk that for 400 meters. So what happens then is you've walked first 10.0 meters due east, and then you took a right and walked 400 meters due south. Okay, this is supposed to be a right angle. Now, if you stop right then, the resultant, or the sum of these two vectors, let's call this vector A, and let's call this vector B. And I'm not referring to the number as being A because that's not sufficient to be the vector. 400 meters cannot be a vector, neither can 10 meters. But 10 meters back, 10 meters east is a vector, and 400 meters south is a vector. So now if you draw a vector that points from where you were at the beginning to where you ended up, that is exactly what we call the resultant. And we usually label R, and in this case, it's A plus B. Okay. Again, this is not that good of a drawing, but the important point is you see that when the vectors are head to tail, see the head of this one is at the tail of this one. When they're head to tail, you just draw a vector from the tail of the first to the head of the last. So this is the head to tail method. Okay. And if you had 3 vectors, you just do from the head of the first to the tail of the third. I mean, excuse me, from the tail of the first to the head of the third. And if you had 50 vectors, you do from the tail of the first to the head of the 50th. It doesn't matter, no matter how many you get. And in fact, you can actually see if you first walked due south 400 meters and then due east 10 meters, you'd still end up at the same place. So not only is R equal A plus B just given by that, but now we see that A plus B is equal to B plus A. And the associative property is okay as well. So for instance, you could say A plus B, do those first and then add C. Or you could do A, adding it to B plus C after you did B plus C first, and you still get the same thing. Okay, so that's me telling you about the multiple vectors and how it doesn't matter what order you take them in. You can take them 2 at a time, 50 at a time. But if you're doing it graphically, again, using a protractor and a measuring device and a really precise pen and coordinate systems and all that good stuff, you will get a fairly precise answer. Okay. Now, what if the two vectors are tail to tail? So when they're tail to tail, okay, I'm going to draw two vectors tail to tail. In this case, I'm going to say vector A is this one. And I'll say vector B is this one. Well, the nature of vectors are, assuming you're not dealing with vector fields, you're just dealing with individual vectors, then you're free to move this vector anywhere you want, long as you don't compress it or stretch it. In other words, you don't change its magnitude, and as long as you don't twist it, i.e. change its direction. So those are the two important parameters. If you don't do any of that, you're fine. So you can actually imagine this vector B being like with a little loop on the end that allows the vector B to slide along A. And as long as you don't twist it to change its angle or stretch it or compress it to change its length, you're golden. So I could actually, in principle, move this vector, slide it along here, and then draw it just like it's head to tail, right? So now it's looking like head to tail, and you know how to do head to tail. You go from the tail of the first to the head of the last. And because of this, it doesn't matter which one's the first and which one's the last. Now, alternatively, you could also put this one and imagine it having the little ring, and it slides along this one like that. So either one of those, this being A plus B, this being B plus A, they both give you the same result. And that is the vector that starts at the common tail and ends at the diametrically opposite corner. Okay, so this is R, which equals A plus B. So if you need to add vectors head to tail, you just put them all head to tail. You draw a vector from the tail of the first to the head of the last. That gives you the resultant. If they're tail to tail, you just complete the parallelogram. So notice this is supposed to be exactly parallel to that. And this is supposed to be, it's not, I didn't draw it that well, but it's supposed to be exactly parallel to that. And then you just go across from the common tail to the opposite corner, and that's the vector R. Okay, so that's how you add vectors graphically. Again, if you are very precise using protractors and rulers, you can get very precise results this way. If you're so precise as to use AutoCAD, then you can get exactly the right answers. Anybody have any questions on that? All right, now let's go to subtraction. This time I'm going to start with tail to tail instead of head to tail. And you'll see why in a second. So subtracting vectors. I'll just call it subtraction. So let's say the vector A minus B. Now, here's one of those stupid rules you learned in algebra. And it helped you, for instance, when you were doing signed numbers, when you had numbers with positives and negatives, because from that you learned that minus a negative is the same thing as plus a positive. And in fact, what it says is that the subtraction is defined to be the sum of A and the opposite of B. But now, since we did this stuff at the top with positives and negatives being multiplied by vectors, now we can see what that negative B means. So if I take these two vectors, let's say A and B, this time I'm going to draw B this way. If I take those two vectors and want to subtract them, I realize that I have to actually deal with A minus B, because it's A plus the opposite of B, which is negative B. So all I have to do to make negative B is put the head at the opposite end, then I'll get negative B. But now look, negative B is actually head to tail with A. So I know exactly what to do, because I know once I have negative B, I just add them. So in fact, A minus B will be this wonderful little vector right here. So you see that when they're tail to tail, they're really easy to subtract. Whereas when they're head to tail, they were really easy to add. When they were tail to tail, they were kind of a pain to add because you had to complete the parallelogram. But now you see when they're tail to tail, subtraction's easy. Now let's look at head to tail when you're subtracting them. So again, let's draw our A and B vectors, but this time I'm going to draw them head to tail. So I will do A just like I had before, and I will do B sort of like I had before. So what I want now is A minus B, which we know is A plus the opposite of B. So that tells me I'm going to have to draw the opposite of B. Well, that's not very helpful. I have two vectors tail to tail, head to head. That's kind of crazy, right? Well, that's okay, because if I slide this vector along here, and I'm trying to keep it, of course, perfectly parallel, then I'm creating that parallelogram again. Similarly, if I slide this vector along here, I have completed the parallelogram. Okay. So now you can see that if I were to put negative B over here, now I can see that the subtraction is in fact going from the opposite corner to the common head. So that's how you subtract two vectors when they're head to tail. So I've actually given tests where I'll just draw two vectors on a piece of paper, either head to tail or tail to tail, and say, what is A minus B? Or what is A plus B? So that's a completely fair question. It's something you should be able to do. All you have to do is know whether you're going to complete the parallelogram or you're just going to draw from one end to the other. This is the model of how you do all that. Any questions on that? Okay. So we've now done a robust series of examples of how to graphically add vectors. What I want to do now is actually add 4 vectors. Okay. So let's see if we can do that. I am going to start by drawing a coordinate system. Now, everybody's coordinate system will be different, and that's perfectly okay, because in reality, the vectors exist with or without coordinate systems. The coordinate systems are something we just use to make it comfortable for us. So for instance, in my space where I'm looking right now, this is the positive X direction, and this is the positive Y direction. Now, if I happen to go to 30 degrees south latitude, then this X direction is going to become this. And this is going to become the Y direction for someone at 30 degrees south latitude, 36-ish roughly. Okay. So those two coordinate systems are entirely different. They're at 90-degree angles to one another, but lo and behold, it won't matter, because what's going to happen if I say a vector is 30 degrees east of north, then I'm going to take my right and my up, and I'm going to pull out a protractor and measure up 30 degrees, mark off that line, and then, you know, draw it to make the line at 30 degrees, and then erase it down to the length that it needs to be. And that person at the other place is going to do exactly the same thing. They're going to measure theirs at 30 degrees. And long as they stick to their coordinate system and I stick to my coordinate system, we're all going to find the same right answer. Okay. So again, that's part of the beauty of vectors. Oh, I don't know why I turned that off, but here I am. Okay, I turned it back onto the document cam. So what I'm going to do is try to draw a coordinate system. And I am going to draw the coordinate system like this. This one I'm just going to keep in 2 dimensions. I'm not going to try to mess around with 3 dimensions. Okay, and I'm going to take some vectors. I'm going to say vector A is going to be, let's say, vector A will have a magnitude of 20.0 newtons, and it's going to be at an angle of just plain 30 degrees. Then I'm going to say vector B has a magnitude of 25.0 newtons, and that's going to be at, let's say, 53.1 degrees, and that's going to be west of north. I'm going to say vector C has a magnitude of 28.28 newtons. And that one's actually going to be at, let's say, 225 degrees compass heading. Okay. And then finally, vector D, that's going to be, let's say vector D is going to be 15.0 newtons at, see if I've done everything. Let's do this one's going to be 36.9 degrees, and that's going to be south of east. Okay. Now you might notice something. I'm trying to use those very special triangles. Okay, that'll help me out. But what I don't want you to do is I don't want you to be that person that just says A sub x is equal to magnitude of A times the cosine of theta, because that doesn't work. In fact, it can work, but only if you always use this one. And even then, if you don't know your trig functions well, you're going to get mistakes. Because guess what? The trig or the tangent of, let's say, 225 degrees is exactly the same as the tangent of 45 degrees. But when you take the tangent of 225 degrees, that should give you x and y components that are both negative, Whereas when you take the tangent of 45 degrees, that should give you X and Y components that are both positive. So because of that, I don't recommend doing that. I recommend you always choose the smallest angle between the vector and the actual nearest coordinate axis. And then you decide the signs, and then you decide what angle to use, and then you decide what trig function to use to get each component. So I'm going to first draw A up here. I've got A is supposed to be 20 newtons, and I'm not even going to try to draw it to scale. You can see on my world's greatest vector problem that's listed on my YouTube channel, but it's also linked on our Canvas module for this week. You can see how to actually do it with great detail. I'm just going to realize that these are all pretty close to the same magnitude, and I did that on purpose. And I'm going to say that's about 30 degrees. Remember, when it doesn't say anything else, if it's positive, it's supposed to be measured counterclockwise from the x-axis. So I'm going to call that A, and I'm going to say this is 30 degrees. Then I'm going to see B as 25 newtons. That should be slightly longer than this. In fact, 25% longer than this one, but it should be at 53.1, which I'm going to say is roughly this angle west of north. So 53.1 is this angle. Now C is supposed to be 225 degrees as a compass. Well, when you're in a compass, dealing with a compass, north is up, as is 0 degrees, and east is to the right, as is 90 degrees. So this would be 180. 225 would be another 45 this way. And that one's supposed to be about 28.28. So that's going to be a little longer than that last one, only it's essentially at 45 degrees. So I'm going to say this is C, and this angle right here is 45 degrees. And that happens to be exactly the angle that they're referring to. 225 would be 180 plus 45. Okay. And then finally, we're going to look at vector D, which is supposed to be 15 newtons. So that should really be about 3/4 the length of this guy, but it's at 36.9 degrees south of east. So I'm going to go something like this and say this is 36.9 degrees. Notice that is south of east, and that's vector D. Now what I'm going to use is the idea of stoplights. Stoplights are green when they want you to go, so I'm going to call positive unit or positive components green and negative components red. So this X component of A is going to be positive. The Y component of A is going to be positive. So this is A, Y, and this is A, X. This Y component of B is going to be positive, but this X component is going to be negative. Okay. This X component and Y component are both going to be negative. So this is C sub Y. And this is C sub X. And this Y component is going to be negative. That's D sub Y. But this X component, which I could actually draw over here as well. In fact, I think I will, just to keep it from getting messy. So this is D sub X, and that's going to be positive. So now what I recommend my students doing is don't try to take the training wheels off yet. You know, take each one of these vectors, and let's say A. Here's vector A. I'm going to write sine of 30 degrees, and I'm going to think some old horse came hopping through our alley. some old horse came a hopping through our alley, or so ka toa. Either of those are fine. And I'm going to say, well, sine 30 must be opposite over hypotenuse. So that's going to be AY over A. And cosine 30, that's going to be adjacent over hypotenuse. So that's AX over A. So I'm going to say A sub X. Notice it's positive, so I'm going to put my positive sign there. And I'm basically going to take the magnitude, which is 20 newtons, and I'm going to multiply it by the cosine of 30 degrees to get the actual number, the size of this. Well, the cosine of 30 degrees, you can see is 1.732 over 2, which is 0.0866. So I can just multiply 0.0866 times 20, which notice the 2 is gonna would have canceled out with the 2 to begin with. So basically, when I multiply 20 times the cosine of 30, I'm going to get 17.32 newtons. Similarly, when I do AY, that's also positive, so I'll force the positive sign right there. And now cosine, or excuse me, sine of 30, you can see is opposite over hypotenuse. That's just 1/2, and 1/2 of 20 is 10.00 newtons, say. It actually, I should be carrying only 3 sig figs. So I'll put it like that. Now I'll do the same thing with B. But like I said, I'm not going to take the time to write what the sine and cosine is. I'm just going to go ahead and jump to B sub X. And I can see B sub X is negative, so I'm going to force a negative there. And I'm going to say it is 25.0 newtons. In this case, it's times the sine of 53.1 degrees. And of course, the sine of 53.1 degrees is opposite over hypotenuse. That's 4/5 or 0.8. Well, if I divide 25 by 5, I get 5. And then times 4, I get 20. So this is going to be negative 20.0 newtons. Okay. Any questions on that? Again, this is something you should be doing with your calculator at the same time and verifying my work. Now, BY is actually going to be, yep, BY is going to be positive. Notice I had the positive there. Cosine is actually touching, or excuse me, the angle is actually touching it. So that tells us the Y component is going to be given by cosine. So I'll put 25.0 newtons times the cosine of 53.1 degrees. Cosine of 53.1 degrees is in fact equal to, if I look back on my 3, 4, 5 triangle, cosine would be 3/5. So if I do 25 divided by 5, that gives me 5 again. And then times 3, that gives me 15. So this is positive 15.0 newtons. Now my C vector, I'm going to say CX. Notice it's negative, so I'm going to force a negative there. And in this case, it doesn't matter whether I use sine or cosine because the angle is 45 no matter what. And in fact, it's 1 over the square root of 2, which is basically 1 over 1.414. Okay. So in this case, I'm going to do 28.28 newtons times, since I'm doing CX, I'm going to use the sine of 45 degrees. Now, you probably recognize this as 20 times the square root of 2. And then sine of 45 is 1 over the square root of 2. So this should just become negative 20.0 newtons. CY is also negative. That's going to be 28.28 newtons times the cosine of 45 degrees. Cosine, of course, is 1 over the square root of 2. This is 20 times the square root of 2. So again, I get negative 20.0 newtons. Again, just by choosing those special angles, I'm managing to do all this without any calculator help. Then finally, I'll say vector D, and vector D gives me D sub X, which we decided was in fact positive. So I'll force a positive sign there. D sub X is 15 newtons, which I think you'll recognize as 3 times 5. So when we talk about our 3, 4, 5 triangle, it's 3 times 5, 3 times 3, and 3 times 4. So I'm going to now take that, and to get the X component, I'm going to take the cosine of 36.9 degrees. Again, that's going to be positive, and of course, the cosine of 36.5 degrees, 36.9 degrees, excuse me, the cosine's 4/5, right? So basically dividing that by 5, you get 3. 3 times 4 is 12. So this one will be 12.0 newtons, and the other one's got to be the 3 times 3, which should be the 9 newtons. Now the dy, that one's definitely negative, so that's going to be 15.0 newtons. And this one I got to use the sine trig function of 36.9. And of course, the sine trig function of 36.9 is 3/5, like I said. So it'll be 3 times 3, which is 9.00 newtons. That's how you what's called resolve a vector into its components. You take the vector and you use trig functions to figure out for a given coordinate system, what's the X component, what's the Y component. So going this way is resolving vectors into components. The reason why is it turns out that geometric stuff I showed you just results in R sub X being A sub X plus B sub X plus C sub X plus D sub X. In other words, it's sort of like algebra. If you remember the IJK or the X hat, Y hat, J hat, K hat, excuse me, X hat, Y hat, Z hat notation. It's just like only adding like terms. So you couldn't add an I hat with a J hat. Similarly, you can only add AXs with BXs and CXs and DXs. So if I add AX and BX, I get 17.32 minus 20, which I'm going to remember that my arithmetic stinks. So 17.32 minus 20, and then minus CX, which is another 20, and then plus DX, which is plus 12. I'm actually doing addition on all these, but the negative ones automatically become subtraction. So I'm doing plus 12 now. So I ended up doing 17.32 minus 20 plus 12. And I got negative 10.68 newtons. And I'm carrying one extra sig fig there. So just a refresher, this is 17.32. This one is negative 20. This one is negative 20. And then this one was 12. Okay, so showing what everything got there. Let's make sure that does make sense. My X component of D was supposed to be positive. My X component of C was supposed to be negative. My X component of B was supposed to be negative. And my X component of A was supposed to be positive. So that all looks good to me. Now, similarly, the resultant Y component is A sub Y plus B sub Y plus C sub Y plus D sub Y, which is going to be 10.0 newtons plus 15.0 newtons minus 20.0 newtons minus 9.00 newtons. So 10 plus 15 is 25, minus 20 is 5, minus 9 is negative 4.0 newtons. I could have added another 0, but that would have been an extra sig fig that we are not justified So that's what I got for my two vector components of the result. Now, I was given these vectors in magnitude and direction format. So my rule in my class is if I give you vectors in magnitude and direction format, I expect them to come back in magnitude and direction format unless I specify otherwise. Usually what I do is I ask you for both. So in this case, I'm going to say R, which equals A plus B plus C plus D, is going to be equal to negative 10.68 extra digit newtons I hat minus 4.00 underline Newton J hat. That is a correct answer, but I want both formats. So now I want to show you how to build a vector from its components. This was resolving, this is building. So now I'm going to draw my XY coordinate system again. And notice my X component is almost 11. And it points in the positive direction. So I'm going to say, here's my X component. Oh, excuse me, it's supposed to be negative. That is not my X component. I did not do that. Y'all can't pin that on me at all. Okay. The one I worked earlier actually had positive X component, but a negative Y component, I think. So that maybe that's what I was doing. I don't know. All right. So this is going to be my X component, which is 10.68 newtons long. And the 8, of course, is an extra.
We can't see digit. It.
Oh, thank you. The 8 is an extra, is actually an extra doubtful digit. Now the Y component is a little bit more than a third of that, and that points downward as well. So I'm going to say the Y component is roughly this. Okay, again, I kept the green because it was supposed to be positive, but the green's not showing up that well anyway, so I'll put it red like this and red like this. This one's 10.68 newtons, and this one's 4.00 newtons that way. So what that means is our actual vector R is like that. So I'll call this angle theta, say, and I'll say that theta is equal to the inverse tangent of opposite over adjacent, remember, through our alley. So that'd be 4.00 newtons, carried 1 extra sig fig, over 10.68, carried 1 extra sig fig newtons. The newtons cancel out. I take the inverse tangent of that. Four divided by 10.68 gives me 20.53 degrees. Now, technically, I only have 2 sig figs there and 3 there. So both of these are extra. So I should really call that 21 degrees. Now, the magnitude of R is just given by the Pythagorean theorem. It's the square root of 10.68 newtons squared plus 4.00 newtons squared. And when I do that, I'll say 10.68 squared plus 16. And of course, now I got to take the square root of that. And with that one, I get, oh, I don't know what I just did, but anyways, that one I get 11.40 newtons. Now, technically 10.68 squared is actually equal to 114, but that's supposed to be only 3 sig figs. So that's only to the nearest whole number. And 16 is actually supposed to be 2 sig figs. So that should be to the nearest whole number. So really, I should only round that to, that'd be 11.411. So I really should only be rounding that to the nearest whole number. So that one should be like that. But what I'm going to call it is I'm going to say R is equal to 11.4 newtons. And I'm going to say that is at, using the convention of measuring counterclockwise from the positive x-axis, I do 180 there. So there's going to be 201 degrees for that. So those are my answers for adding those 4 vectors. Any questions on that? All right, well, that's all I really wanted to get done with you guys tonight, is make sure I got through that. So even though I started 5 minutes late, I can still let you go on time in case someone has a class right after this. I think someone did for some reason. That's what I seem to be recalling. But the main thing is I got through that part, which is critical in my estimation for me to keep up pace. I need to be able to get to that point on the first lecture. The rest will be nothing but projectile motion, and we'll study it basically using a wonderful R position vector, not to be confused with this R. We'll just use lowercase r position vector, or sometimes you could use X and just realize it has an X, Y, and Z component. But we can do that. Does anyone have any questions on any of this before you go? So this is definitely a skill that you'll be doing on your first day or this day of your calculus-based physics course. And you'll do it on the last day of your calculus-based physics course. And I suspect you'll do it in the last day of many engineering programs, bachelor's degrees, as well as any physics or astrophysics degrees. So it's not something that's going to go away. So make sure you learn it. I know there's a simple way to do it with a calculator. That's not going to be good enough. I'm going to ask that you be able to, in some cases, find me the components that I want. Tell me whether they're positive and negative and all that good stuff. So don't rely on that neat new fancy calculator doing adding of vectors for you. Even though it can, that's good when you're, in the real world working. But right now, we got to know that you know how to do it. So everybody's free to go. I'll stick around and wait for anybody to have questions. Thank you for coming, everybody. So Aaron or Hassan, do you have any questions? Or Jarrett, Mario, Nate?
Yeah, I actually have a question. I took the practice test a couple of times. There was a specific question about like the ball and the flagpole. And I couldn't seem to grasp completely what.
You want to show it to me by sharing your screen?
Yeah, I can do that. Can you see it?
Okay, determine I have a flagpole. Amy throws the ball straight up and times it. She sees that the ball goes by the top of the pole after 0.5 seconds and then reaches the top of the pole again after an elapsed time of 4.1 seconds. How high is the pole above the point where the ball was launched? Okay, so what we have here is 2 times at which the height was equal to the height of the pole.
Okay.
So what you could do is you could use x equals 1/2 at squared plus v0t plus x0, that equation, using t equals 0.5 seconds, not knowing what the initial velocity is, but then doing the same thing using t equals 4.1 seconds, again, not knowing what the initial velocity is, that would allow you to eliminate the initial velocity, and then you could ultimately solve for the time. So that's one way you could do it. I'm trying to think of a better way. You do know, for instance, by the symmetry of the problem, that the ball should have the same speed, which in this case is magnitude of velocity, at the t equals 0.5 and the t equals 4.1 second time interval. So that's something else you could use. But I don't think that works out too nicely. So yeah, I would probably try the x equals 1/2 at squared. So x, you're going to let that be the height of the actual flagpole. And you're going to say h is equal to negative 9.8 t squared plus v0t. And you're going to do that one time for t equals 0.5. And then you're going to do that another time for t equals 4.1. And if you add those two equations, or actually, let me write it down for you real quick. 0.5 and 4.1. Yeah, let me steal the screen back from you and I'll show you what I'm talking about. It's a lot easier to write than it is to say, or at least to hear. Okay. So I'm saying you're going to use x equals 1/2 a t squared plus v0t plus x0. We're going to say the top of where the girl threw it, the height was 0. We don't know what velocity she threw at. I'm looking again, you're looking at my head. Dang it. Sorry. So we don't know what this is, but we don't really care to know it. So I'll put a question mark over it, but I'll put quotation marks around it because I really don't want to know, right? I'm going to call this the height, and that's what we want to know, but I don't put any quotation marks around that because I really want to know that. So what I'm going to say is h is equal to negative 1/2 times 9.80 meters per second times t, which in this case I'm going to say 0.5 seconds squared, plus v0 times 0.5 seconds. Now I have another equation. H is equal to negative 1/2 9.80. The negative is coming from g pointing downward. Meters per second times 4.1 seconds squared plus v0 times 4.1 seconds, like this. Okay, so we've got those two equations. Now if you multiply this top equation by 8.2, let's make it negative 8.2. Okay, then you'll get a new equation that'll be negative 8.2h equals, now this 1/2 times 9.8 becomes 4.9. So when I multiply 4.9 negative times negative 8.2, I get a positive. I get a positive 40.18.
And what was your reasoning for picking negative 8.2?
Basically, I took 4.1 and divided it by 1/2.
Okay.
So what this is going to become is negative 4.1. So it'll be exactly the same coefficient, but negative. So that when I add the two equations, this v0 will disappear.
Okay.
Okay. So when I multiply this 1/2 times 4.9 times negative 8.2, I get that. Then I do times 4.1 seconds squared. That's going to be 16.81. And this would be seconds squared and that's meters per second squared. So all that turns out to just be meters there, or meters, yeah, meters there. And then this one's going to become, oh, excuse me. Ah, dang it. That's okay. I didn't like the way I handled those units anyway. So what I forgot I was doing was this top one, not the bottom one. The bottom one I'm leaving the same. So this would be 40.18 meters per second times 0.5 squared, which is 1/2 times 1/2, which is 0.25 seconds squared. So I still got to multiply that. I was just carrying out part of it. And then when I multiplied this 8.2 negative times 0.5, that's going to give me negative 4.1 seconds times V0. So now you can see that I can add these two equations, and 1 minus 8.2 would be negative 7.2h is equal to, now I'm going to do 1/2, 9.8, 4.1 squared, negative, and add it with all this junk. So I'm going to say negative 0.5 times 9.8 times 4.1 squared. That's negative 32.9476. And that turns out to be meters. Okay, and now I'm going to add that to the 40.18. So I'm going to say plus 40.18 times 0.25. I get negative 22.9026. And this turns out to be meters as well. And notice V 4.1 minus 4.1V gives me 0. So I can now see that H is going to be basically negative 22.9026 meters over negative 7.2 meters. So that gives me about 3.18 meters. Not very tall. Notice negative divided by a negative gives you a positive. So that's a way to do it. Of course, I've been doing this kind of thing for decades. So there's probably a lot of other ways that might take a few more steps. I think that might be one of the quickest ways you could do it.
Okay. All right. Thank you.
No problem. Hope that helped. How about you, Nathan or Rebecca?
All good. I just wanted you to work, or wanted to see you work that out. So thank you.
You're welcome. Have a good one. Nothing for you either, Nathan? All right. Well, I'm going to call it a day. Good evening, everyone. Have a nice night. Thanks again.